In the last few lectures, I showed you how, let's say, the mechanics of mesh refinement work in terms of, let's say, if you want to refine this cell, how do you produce transition elements, let's say through red-green refinement, in such a way that you always end up with a mesh that you can work on. And then I showed you how we do this in step 6 in the first tutorial program in deal.II, where we actually do have an adaptive mesh. What I want to do in this lecture is to show you a little bit more, let's say, from the mathematical underbelly of this. Because one of the things that we haven't talked about is, let's say, how do we decide which cells we actually refine? And there are two parts to this question, namely, can we come up with a, let's say, numerical indicator for every cell that determines whether, or that tells us something about whether it's useful to refine here or there. And then the second step would be, once I have all of these indicators for every cell that let's say, gives us an idea how big the error might be on that cell, that I have to decide which of these cells I actually want to refine. So in this lecture, I want to introduce you to, let's say, the simplest and probably most widely used refinement indicator that helps us make these sort of decisions. It's called or it's commonly called the Kelly error indicator. And so I want to show you a little bit of, let's say, how do we get there, what are the mathematics behind this, and how is it defined. And then in the next lecture, I'm going to show you the other part of the question, namely, once I have computed for every cell in my mesh what the error might be, or some kind of indicator how useful it would be to refine the cell. The next step then is to decide which cells actually to refine. So we typically call these the estimate and the mark phase. The estimate gives us an indicator for every cell, and the mark determines which cells are marked for refinement. And then once we have marked, then we actually do the refinement, and that's what I showed you in these earlier lectures for triangular meshes and for quadrilateral meshes. So the question that I want to answer in this lecture that I call 17.25 is how to derive simple refinement indicators. And the reality is that this lecture is actually just about one simple refinement indicator. So let me start with this picture here that I've showed you before, and that I'm going to show you probably several more times in this and other lectures. So this is a simulation that we did with a code that is based on deal.II that is called Aspect. It shows a section of the Earth. The Earth is composed of layers, so we're sitting somewhere out here on the surface, and then there's the core underneath, and the area in between is the mantle. And the core is pretty hot, the surface is pretty cold, so you have a hot layer here, and when you heat material, it expands, so it becomes lighter than the surrounding material, and then you have these sort of plumes that rise up. So intuitively, I think everybody who, let's say, has thought about these sort of questions a little bit would say, well, what we should really do is we should have a mesh that is fine in these areas where something is happening, and then maybe a coarse mesh over here. So you see the mesh over here, so it's coarse here, and it's fine only really to resolve these sort of plumes. And let's say when we talk about this in our community, we often say that, well, you want to have the mesh fine where something is going on or where something is happening. And I think this mesh really illustrates that. But there are two questions I think that are worth asking, namely, why is that so? Why should we have the mesh fine only in places where something is happening? And the second question then is, well, so how do we actually determine this? So what is a, let's say, numerical criterion to determine whether something is going on in a cell? So if I ask myself the question, should I refine this cell here or one of these here, for example, what are the ways how I can say something is going on here? And so this is the topic of this lecture, where I want to talk a little bit about, let's say, strategies to address this. So I've mentioned this in lecture 16 already, that for many equations, and certainly for the Laplace equation, I can often show something of the following kind, namely that the error in the H1 norm, so the error is the difference between the exact solution and my numerical solution, and the H1 norm measures the gradient, so it is the integral of the gradient of the error squared and integrated over the entire domain omega. That I can show that this quantity is bounded from above by some constant that I may or may not know, it's not all that important, times a sum over all of the cells times the square of the mesh size times the H2 norm of the solution on this cell. And you will notice that I have squares everywhere. If you want to take the square root on both sides, and then you really just have the H1 norm, and you immediately see that, let's say if I ask the question, what is the biggest of these HKs? That's HK is the diameter of cell K. If I take the biggest one, I can estimate that from above by just H squared, and then the sum of the H2 norm squared on the cells just gives me the global H2 norm. So what I have here, if I take the square root on the left and on the right, is just the usual first order convergence of the H1 norm. So this is sort of a statement that is true for many equations. If I have linear elements, for example, then that would typically be true. For quadratic elements, I should say that you should get h to the 4, but then I need to have the H3 norm here. So I'm not so much interested about this latter part here. In this lecture, I really care about the fact that I can write the total error as a sum over the cells of terms that are local on every individual cell. So we talked about this, I think, in lecture 16, that the optimal strategy, if I define the error or an upper bound for the error on every cell as just CHK and then the H2 norm, so that's the square root of this term here. If I define it like this, then the optimal choice for the mesh size is that is so that I equilibrate these error indicators. So equilibration means that I want to choose my mesh size in such a way that the error indicators or the error estimates on every cell have the same size. That turns out to be the optimal strategy to minimize the error while keeping the problem as small as possible. Okay, so how do I do this? So if I, in essence, if I look at this criterion here, then I need to figure out what the H2 norm, that is the second derivatives of my exact solution, are on every cell and integrate it over every cell. So when I say something is going on, what I really mean that the second derivatives are large. That is, so I want to stress this is the case for linear elements, right? For quadratic elements, it is important to estimate something like the third derivatives. But let's stick with linear elements for the rest of this lecture. When I say something is going on, I mean that the second derivatives are large. I do want to make sure that we agree on the notation. So when I say that I'm looking at the H2 norm of the solution, that is the integral, so the square of the H2 norm is the integral over the domain, in this case the cell, of the solution squared plus the gradient of the solution squared plus the second derivative squared. So the H2 here indicates the highest derivative, and then there is something that we call the H2 semi-norm. That's the thing that really appears here on the right. The H2 semi-norm only integrates the second derivatives of u. So as I mentioned, when I say something is going on a cell, what I really mean is that the second derivatives are large. So this was this sort of came out of the blue. I want to spend the next few slides on deriving this quantity briefly. So this estimate here, that's sort of the key estimate that's going to inform us about, let's say, the size of the error, and I would like to explain a little bit where that comes from. So in order to derive this, let's look at the Laplace equation. For simplicity with zero boundary values, but that's really not important. So the Laplace equation is minus Laplace u equals f, zero boundary values, and you've seen this many times. The weak formulation of this is find a u, so the gradient u, gradient v equals f times v, and so when I have these parentheses, I always mean the integral of grad u, grad v dx, right? So this is the continuous formulation, and then the discretization would be choose a finite dimensional subspace VH, so that's our finite element space, for example, and I want to find a UH in this VH, which is a subspace of my function space H10, so that gradient UH times gradient VH equals F times VH for all test functions VH, right? You've seen this many times. That's the standard approach to finite elements. So let me write down these two equations, one atop the other. So there's the continuous equation here, and there's the discrete equation. The continuous equation has to hold true for every test function v in H10, for example. And because my test space VH is, my finite dimensional space VH is a subset of V, that means that the first equation in particular also has to hold true for every V that is from VH. So for every discrete test function, the first equation is still true. So I can say gradient U, gradient VH equals F comma VH, and gradient UH, gradient VH equals F comma VH, and then I can subtract these two equations from each other for a choice VH. The right-hand sides are exactly the same, so they give me a 0. And then here I have, this is not what I wanted, here we are. So here I have the gradient of U minus the gradient of UH, and that gives me exactly U minus UH, so that's the error, right? So we call this property that the gradient of the error times the gradient of VH equals 0. We call this Galerkin orthogonality. And I want to explain just in 3 words what that actually means. So when I write down this bilinear form here that I have here, gradient integral of gradient something times gradient something. So that's this thing here. This defines a scalar product. So you can think of this in terms of vectors, and let me try to explain to you how I think about the finite element solution. So when you look at the finite element solution, it lives in an infinite dimensional space. So I cannot visualize an infinite dimensional space, of course, but I can imagine, for example, that my 3-dimensional space, the studio around me here, that is this space H10 where I can find the exact solution. And then the finite element space, that's a finite dimensional subspace. So if I want to visualize this, maybe I would say that this plane here, that is the finite dimensional subspace, and I'm going to try to find a finite element solution that lies in this finite dimensional subspace of my overall space. So let's say the exact solution lives here, or that's where the exact solution is, in this infinite dimensional space, and the discrete solution lies on the subspace, so let's say over here. So the error is, of course, exactly the vector that connects these two, right? It's U minus UH, so it's the vector that goes from here to here. What the Galerkin orthogonality statement says is that this connecting vector here is perpendicular to the plane. So if I test this vector with every vector that spans my finite dimensional subspace, so if this is my finite dimensional subspace, I could, for example, choose this vector and this vector. Both of these vectors are perpendicular to the error. That's why we call it Galerkin orthogonality. The error is perpendicular, or sits perpendicular to this finite dimensional subspace. That's where that term comes from. And one of the things that is important to realize is that what we call orthogonal is defined by the inner product that we use. So in this case, the inner product is simply the gradient f gradient v inner product. That's the notation that I chose. So gradient f gradient v integrated over, that is the inner product that I choose. And with respect to this inner product, the error is perpendicular to my finite dimensional subspace. So that's what this means when I say gradient E gradient VH equals 0. Okay, so since I since I have this Galerkin orthogonality, let me use this in one place. So if I write down the norm of the error squared, so that's what we call the energy norm for the Laplace equation. That's of course the scalar product of, let's say, integral gradient E comma gradient E. Okay, and if I look at this form here, so Galerkin orthogonality allows me to add a 0. Because I know that the gradient of E times gradient VH, that's 0 for any VH that I might want to choose. Okay, and so if I add this first term and my 0, I'm going to get gradient of E times gradient of U minus UH plus VH. That is exactly the square of the energy norm error for every VH that I might choose. And if this is true for any VH that I might choose, I have the option to choose a particularly convenient one, right? And the one that is particularly convenient to me in this context is that I'm going to choose VH equals my Galerkin solution, the finite element solution, minus the interpolant of the solution. So the interpolant of the solution is that finite element function that coincides with the exact solution at the nodal points. That's the one that I'm going to choose. And so if I plug this in to my equation, then I get this here. So I have that the gradient of U minus UH, so the energy norm error, equals the gradient of the error times the gradient of the difference between the exact solution and its interpolant. So what I need to use next is something that is called the Cauchy-Schwarz inequality. So the Cauchy-Schwarz inequality says that the scalar product of two functions f comma v, I can bound that by the norm of f and the norm of g. You've seen this for finite dimensional vector spaces, but it's the same for infinite dimensional function spaces. So if I use this in this context, I can use this here on the left side. So the gradient of the error squared is less than or equal than the gradient of the error. So I use this up here, right? So I have that here is an inner product, and so this is less than or equal the norm of this times the norm of this, so that gives me this. And I have here the gradient of the error. On the left-hand side, I have the gradient of the error squared. I can divide by this, and I find that the error, the H1 norm of the error is less than or equal than the H1 norm of the difference between the exact solution and its interpolant. So I can put this on its own slide here. So this is the same property that we just had, right? This one here. This is what is often called the best approximation property. So let me interpret this for you. So in essence, this means that in the H1 norm, the error of the finite element solution is at most as large as the error in the interpolation. Right? So the interpolation error would be the difference between the exact solution and the function that, the finite element function that equals the exact solution at the nodal points, but in between is, for example, piecewise linear, piecewise bilinear. So this best approximation property really tells us that the finite element solution is actually pretty good. It is at least as good as something that we could do on a piece of paper, namely if we knew the exact solution connected with piecewise or approximated with piecewise linears. I should also notice this. So this is true for the Laplace equation. For many other equations, that's not exactly true for many other equations. There would be a constant here that depends on the equation. That in this case would then mean that the finite element error is at most as large as the interpolation error times some constant, and we still call this the best approximation property. So there's of course a problem here, and the problem is that we cannot compute the interpolant IHU because we don't know the exact solution U. Nothing on the right-hand side is actually known. I mean, if I knew the exact solution, I didn't have to solve it numerically with finite elements. So this is sort of a statement that's interesting, and we will use it in the next few steps, but let's say for the moment it is not particularly useful because I don't know I don't know U. Okay? On the other hand, of course, the UH, the thing on the left-hand side, the finite element approximation, that is very much computable. So I'm interested in the size of the left side, but I don't know the size of the right side. So what I need to do is I need to look at the interpolant a little bit more. So if you look at the right-hand side, then what you find is that the error in the interpolant, so the gradient of u minus IHU, that is, of course, defined in exactly this way, and I can break this down into individual cells. So that's just writing the integral as a sum of integrals over the cells. And intuitively, if you just look at this picture, so let's say the black here, for example, that would be the exact solution, and the red is the interpolant, so it equals the exact solution at these nodal points, and in between it is piecewise linear. So you can see already here that the red curve is close to the black curve in those places where the black curve does not have a lot of curvature. Okay, so in particular, let's say if you think about a place where the black curve would be linear, then the interpolant, the red curve, would be equal to the black curve. Whereas in places where there is a lot of curvature, let's say down here, then the red and the black typically do not coincide. And so intuitively, this already tells us something, namely that the error between these two is large where the second derivative, so the curvature of the exact solution, is large. And of course, that's exactly what I've been saying all along, right? That the error is bounded by the interpolation error, and the interpolation error has something to do with the second derivatives of the exact solution. That's what we've always had in all of the formulas that I showed you earlier. So if I look at the interpolation error some more, there is a rather famous lemma by Jim Bramble, who used to be one of my colleagues here at Texas A&M, and one of his students, Hilbert. And so this goes by the name Bramble-Hilbert lemma, and in essence it says the following. So if I look at the error on one cell, okay, so if I look at the gradient of the difference between this exact solution and the interpolant on one cell K, then I can bound this in the following way. So this is some constant, that we call an interpolation constant, times the mesh size times the second derivative. So that's just really a rephrasing of the statement that I made intuitively on the previous slide. And if I add this all up on all of the cells, then I get exactly the statement that I had previously had. So the interpolation error summed over all cells is exactly a sum over all cells times the mesh size squared times the second derivatives of the exact solution. And I can generalize this for general polynomial degree p. So if p is bigger than 1, then I get something like this. And actually, this is not quite true. I think I need to fix this in these slides because I take the square here. It is not p plus 1, but it is in fact 2p over here. So for a quadratic element, I would get h to the 4, and if I take square roots on the left and the right, then I get h squared here. But the point is that I need to take the p plus first derivative of the solution, so the hp plus 1 norm. So if I put this all together, then I get exactly the statement that I had earlier, right? So I bound the finite element error by the interpolation error, and I bound the interpolation error via the Bramble-Hilbert lemma by exactly this sort of term that has the mesh size squared times the second derivatives of the solution. So we call this an a priori error estimate, and the term a priori really doesn't make all that much sense. It means upfront, or I can say something in advance. You can really only understand this a priori if you understand the opposite of it, namely an a posteriori error estimate. So an a posteriori error estimate is something that I can only do after I have solved the finite element problem. That means an a posteriori error estimate would involve the discrete solution UH. An a priori estimate does not involve the discrete solution UH, but only involves the exact solution. the issue here, of course, is that this is sort of a nice statement. It shows us that the whole thing converges, because you remember that I can bound the whole right-hand side by h squared times the global h2 norm of the solution. And so I know that if I make h, my mesh size, smaller and smaller and smaller, it will converge, because I can make the right-hand side smaller and smaller. But I don't know anything about the size of the right-hand side, and as a consequence, I do not know anything about the size of the actual error, because I don't know what the right-hand side is. It involves the second derivatives of an unknown solution u. So what I would like to do is I would like to use this and somehow use it to, let's say, first heuristically derive something that I can actually evaluate. Something on the right-hand side, I want to replace the right-hand side by something that I can evaluate. And in order to do this, I want to split the total error into the cell-wise indicators. So I'm going to write the total error as a sum over cells of ek squared. And I'm going to define these EKs, the local estimates on every cell, as HK times the norm of the H2 norm, the norm of the second derivatives. So I call these the cell-wise error estimators. And as before, you recall that my goal is to equilibrate them, so I want these EKs to be roughly equal on every cell, and I can achieve that if the mesh size is proportional to 1 over the second derivatives. So, because I cannot compute these EKs because they involve the exact solution, what I need to do is I need to approximate it. And of course, the idea that one naturally has is that I want to approximate it by replacing the exact solution u here by the discrete solution. And then, as you will see, is I will also have to approximate the gradient by some discrete something that helps us compute something like a second derivative. The question is, of course, how do you do this? So the first idea you might have is, well, I mean, I want the second derivatives of u. Why don't I just take the second derivatives of UH? And that's not going to work. That's easy to see. So if you look again at the picture of the exact solution in black and the discrete solution in red, you will see that the discrete solution is just a set of linears that are connected in points where there's a kink. So if you take the second derivatives of this, the first derivative of a linear function is constant, the second derivative is 0. So in almost all of the points, the second derivatives, so the thing that I would want to have up here, is actually 0. And then there are, of course, the kink points, these ones here. Well, so if I take the first derivative, I'm already going to get a discontinuous function. The second derivative is going to be something like delta functions in these places. So I don't really know how to handle this. That's shoddy mathematics if I just take the second derivatives of this, because I would have to define what I actually mean what I mean by this. So this would I could interpret this in terms of delta functions, but then I would also have to say what I mean by how do the delta functions approximate the second derivatives. So a maybe better approach works through a finite difference approximation. So I can say that the second derivatives of my solution, it would be something like, well, let's say, gradient of UH on a cell to the left minus the gradient of the solution on the current cell divided by the mesh size, something of this sort. And if you remember that UH was a linear function, then the gradient, so this is actually on the right, and this is the current function, the current cell. So the gradient on the cell to the right is is constant, and the gradient on the current cell is constant. So the difference between these is, I'm going to indicate this by these square brackets, and we typically call this the jump. So the jump is the difference between the gradient on the left and on the right. And if you go back here, so it would be, let's say, at this point here, it would be the difference between the gradient on this side here and the gradient on this side. That's what I call the jump of the gradient at this point. And that would be something that allows me to, let's say, approximate the second derivatives at least at the vertices, and then I might be able to, let's say, extend this sort of definition to the entire cell. So it turns out that this actually works. So I can approximate the second derivatives by this sort of finite difference approximation, and I can generalize this. You remember what I really needed is the H2 norm, so that's the integral of the square of the second derivatives, and I can approximate this like this. This looks a little bit funny because you would think that I have to divide by h squared, but that's not actually true. I really have to divide only by h. And I need to sum this. So if I integrate this over a cell, I need to sum this over, for example, the two endpoints. So the k is my cell, dk would be the boundary of the cell. So in this case, in 1D, it would be just the two endpoints. So I can do this in 1D, and I can do something very similar in 2D. So in 2D, I could approximate the H2 norm of my solution, so this term here, by something where I integrate over the boundary of a cell. So just like here I have a sum over the two endpoints of a one-dimensional cell, here it is an integral over the boundary. And so here I had 1 over hk to the power of 1/2, so that cancels 1/2 of the power here. Here I get the same power of h. And then what I want to indicate here, so this is the jump of the gradient along the perimeter of a cell, and then I have to integrate over the entire perimeter, the boundary of the cell. Okay. So if you didn't believe me in this slide here, why I need to divide by h and not h squared, there is a simple argument that you can often make to verify that a formula is correct, and that is just look at the physical units. So the exact quantity that I want to compute is this one, ek, right? That was hk times the norm of the second derivatives of u integrated over k. And if I write this out, this is so hk has physical units length. The integral of this term here, so the second derivatives of something is something like d squared u over dx squared. So x has unit lengths. So this gives me a 1 over L squared, which I square, gives me 1 over L to the 4. My dx in 1D has just 1 power of lengths. So I get L to the minus 3 for the entire integral. L to the minus 3 over 2 when I take the square root. So length times length to the minus 3 over 2 gives me a length to the minus 1/2. Okay? And of course, my approximation needs to have exactly the same physical units. I defined it as this. So that was this hk, that is my factor of L. There's a sum. In the sum, I had 1 over hk. That gives me an L to the minus 1/2. The gradient of has length scale has dimensions 1 over length scale squared. So that gives me 1 over L squared, 1 over L cubed to the 1/2. So L to the minus 3 over 2 times L. That gives me exactly the correct physical units, right? Whereas if I had divided here by 1 over h squared, I would get the wrong physical units, and that just from that argument cannot be correct. Of course, there are many ways of getting a formula to have the correct physical units, but in this case, that actually turns out to be not just the correct formula from the physical units perspective, but also mathematically. I can do the same thing in 2D, and in 2D, the only real difference is that I integrate over dx, which is in this case an area element, so that gives me an L squared. And if you go back to my approximation, so I have the gradient, which is 1 over L squared. The boundary element in this case here, so here I integrate over the boundary of my cell, so my dx has only units length, right? So this dx is a one-dimensional dx, whereas up here it's a two-dimensional dx. And if you multiply all of these factors out, you get that both the approximation and the exact formula have units 1, no units. In 3D, you would get that all of these formulas have units lengths to the +1/2. So the formula for the approximation here really seems to make sense. So what I end up with is that if I want to estimate the error in my finite element solution, so I want the energy error here, I can bound this by the interpolation error, and I could have omitted the c. So c for the Laplace equation is 1, but for other equations it might be bigger than 1. And if I use linear elements, so Q1 or P1 elements, then this sort of indicator here really seems to give me, let's say, an estimate of how poorly approximated the exact solution is by my finite element solution on cell K. And that's, of course, exactly what I'm going to use for mesh refinement later. I'm going to say for all of those cells for which eta k is large, these are exactly the cells that I want to refine. Okay, so it turns out that back in 1983, more than 30 years ago now, 4 authors, Kelly, Degago, Zienkiewicz, and of course Babushka. Babushka has been basically the person who wrote all of the first papers on whatever topic in finite element in finite element history you can think of. They wrote a paper in which they stated that not only is this eta k that I just defined some, let's say, heuristic indication of how big the error is, but it is actually something that I can prove is an upper bound of the error. So what they show is that with this eta k, defined like I did in the previous slides, the error is indeed bounded by, now I really need the constant, times a sum over all of these terms squared when I have the squared over here. So in other words, the error indicator that I had for the Laplace equation in Q1 elements really is an error estimator. And I should mention that, let's say, because of this property that it is provable for the Laplace equation, and because it's so easy to implement, almost all finite element codes that allow for adaptive meshes implement this this sort of quantity here to refine the mesh. And so what people typically refer to then is the Kelly error estimator, because the first author of this paper was Kelly. So whenever you hear the word Kelly error estimator or Kelly error indicator, it is always this quantity where for every cell you integrate around the perimeter or the boundary of the cell, and you integrate the jump in the gradient, because that is an indication of the second derivative. And then you just have to appropriately scale this by some power of h. So in deal.II, this is implemented in the Kelly error estimator class, and that's of course exactly what we used in step 6. So I want to end with an observation. So strictly speaking, the Kelly error estimator was derived for the Laplace equation with linear elements. But because it's easy to implement, and because once you have implemented it, it's already there, people have tried what happens if you apply the same kind of criterion to other equations, or when you use higher order elements. And it turns out that you get fairly good meshes if you use this criterion also for other equations and other elements as a refinement indicator. Of course, in that situation, it is not an error estimator. It is only an error indicator, but it turns out that the meshes that you get just happen to have the right kind of property. And that has a lot to do with the fact that what the Kelly estimator really does is it measures the second derivatives, and just from the interpolation argument, we know that the second derivatives are exactly the sort of quantity that we would want to have for mesh refinement. So in practice, we use the Kelly error estimator not just for the Laplace equation and not just for linear elements, but for all sorts of things. And so if you look through the deal.II tutorial programs, for example, you will find that almost all of the tutorial programs actually use the Kelly indicator. Whether that is, let's say, strictly speaking, valid in terms of, let's say, mathematical upper bound for the error or not, doesn't really matter. it produces very good meshes. And so in particular, the mesh that I showed you at the very beginning of this lecture was also produced by this sort of error indicator applied in that case to the temperature field. So the Kelly estimator really has proven to be a rather universal tool. And that's why everybody in the community uses it. But I hope that what you see from this lecture is a little bit of how you actually arrive at this thing. So what's the idea behind this? Well, the idea is that it estimates the second derivative, and that the second derivative is exactly what you need to estimate the error of the interpolation error. And the interpolation error is exactly what you need to estimate the error in the finite element approximation. That's where the sort of argument comes from. So I've shown you a little bit of the, let's say, derivation of how you compute these criteria for every cell that tells you how good the finite element approximation is. So how close is the finite element approximation to the exact solution? That's what we can measure with these eta k's. And so what we typically do then is we solve and we compute these criteria on every cell, and then we have to decide, okay, so out of these 10,000 cells that I have, which ones do I actually want to refine? And that's going to be the topic of the next lecture then.